Okay, continuing on with section 9.2 about intro to probability. One of the major aspects of probability that we need for finance is called expected value. So expected value has to do with taking the probabilities that we calculate, using them to make decisions based off of the likelihood that something good happens, the likelihood that something bad happens, and trying to quantify it with a number. So I'm going to give you a brief introductory video on this, and then we'll come back and discuss the components of pages 14 and 15.
Your friend offers to play
with you involving a six-sided die. If the roll is 1 or 2, they will give you $48. If it's anything else, you have to give them $30. Should you play the game?
Make a decision. Should you play that game? Use your knowledge of probabilities to try to make a good decision here.
Decide whether or not you should play and how to navigate various choices involving probabilities and payouts. We can use the concept of expected value. Expected value is the average outcome of a single instance of an event over the long run. For example, let's say we flip a coin. If it's heads, you get $10. If it's tails, you get nothing. The expected value is $5 because your winnings would average out to $5 per flip. To calculate the expected value for an event, decision, or game, start by identifying each of the possible outcomes and the probability of each. We are essentially calculating a weighted average. For our coin flip example, there are two outcomes: $10, heads, and $0, tails. The probability of each is 1/2. Then, we multiply each outcome by its probability of occurring and add the results. 10 times 1/2 is 5, and 0 times 1/2 is 0. Add them together, and we get $5 as the expected value for a single flip.
Now notice you can't ever get $5 on a single flip. This is an average. So over the long run, if you were to continue to play this game over and over again, you would expect an average of a $5 expected value.
We can use expected value to estimate the outcomes from playing many times. For example, if we played the coin flip game 20 times, we'd expect to end up with 20 times $5, or $100. This makes sense, right? If we play 20 times, we expect to get heads approximately 10 times, earning $10 for each of those heads. Now, let's look at our original example, the game where we roll a die. If we get 1 or 2, we get $48, and if we roll a 3, 4, 5, or 6, we lose $30. The two outcomes are $48 and negative $30. Because all rolls of the die are equally likely, we can add up the payouts for each scenario and divide by 6. In other words, the probability of getting $48 is 2 out of 6, and the probability of losing $30 is 4 out of 6. 48 times 2/6 is 16, and negative 30 times 4/6 is negative 20. We add them together and get negative 4. So our expected value is negative 4. On average, we will lose $4 for each play of this game. The general formula for
So did you choose to play it? Hopefully not, because that definitely does not work in your favor.
Expected value is the sum of each outcome multiplied by the probability of that outcome occurring.
All right, so all this on the top line, that's just saying the amount times the probability of that thing happening. So it's this multiplication plus this multiplication plus this one, and so on until you run out of events.
It's written like this. One additional note: sometimes an expected value in our favor isn't enough for us to participate. This occurs if any of the outcomes are unacceptable to us and we don't have the option to play multiple times. Imagine a $6,000 investment with an estimated 10% chance of getting back your $6,000 plus a gain of $200,000, 10% chance of getting back your initial investment of $6,000 and coming out even, but an 80% chance of losing the entire $6,000. The expected value is $15,200, which is substantial, but you may not want to open yourself to the most likely outcome of losing $6,000.
Okay, so when you calculate expected value, it is not necessarily the only thing that you should go with, but it is giving you a mathematical a quantifiable outcome that you can use to decide, to help you make an informed decision. All right, so back on page 14, let's look at this example, and this is a fairly simple one. Propose a bet, roll a die, odd number gives you that many dollars. If it's an odd number, no. Yeah, okay, so the winners, this is not written right. The winners are the odd numbers, and the losers are the even numbers. That should be fixed there. So if it's an odd number, he'll give you that many dollars. If it's an even number, you have to pay him that number of dollars, should you accept. Now, you can probably just go off of intuition here and realize the even numbers are bigger than the odd numbers. So you probably don't want to be forking over bigger numbers than you bring back. But just to go through it mathematically, this is going to be the way it works. Every outcome on a die has an equal probability of happening. They're all 1/6. So if you multiply 1/6 times the value of rolling a 1, which is +1 in your favor, and then you multiply 1/6 times the value of rolling a 2, which would be -2 against you, then 1/6 times 3, 1/6 times -4. So each of these multiplications is showing what happens if that thing occurs. 1/6 of the time you're going to roll a 1, and when you do, you get $1. 1/6 of the time you're going to roll a 4, and when you do, you lose $4. So each of these is showing a different outcome. Okay? You do all those multiplications, you add them all up, and it comes out to -0.5. That kind of makes sense that we come out negative because, again, we're subtracting bigger numbers than the ones that we're adding. So this expected value is negative. Bet is not a good deal for you. On average, you're going to lose 50 cents every round you play. And so you're going to kind of bleed money here. So that's not a great idea. All right, another example on the next page. Prize wheel from the previous activity. Actually, you haven't done that activity yet. The Desmos prize wheel, that's coming toward the end of the period today. But this is the breakdown of it. So you can see they are not equal sections like the die roll was. So this is more relevant when we're calculating expected value in scenarios where the outcomes are not equally likely to happen. So remember, we're going to multiply the probability times the event. So let's talk about orange first. There's a 25% chance of orange occurring. And when it does, we gain $1. All right. There is a 3% chance. No. Wait a minute. There's a 10% chance of green happening. So we're going to multiply 0.10 by the amount that we gain when that happens. So that's $20. Okay, red. We have a 25% chance of red happening. And when it does, we gain $4. There is a 15% chance of blue happening. And that is a $10 gain when it does. And there's a 25% chance of purple happening. And there's a $3 gain when that happens. So if we multiply all of these outcomes, we can then simplify it. So multiplication here would give us 0.25. Multiplication here would give us 0.2. Multiplication here would give us 1. Multiplication here would give us 1.5. Would give us 1.5. I have to go back to this one. This is not 0.2. This is 2. Let's fix that. Okay. Multiplication here, we got the 1.5, and then here is going to give us a total of 0.75. Okay, so then you just add those up, and our total comes out to 5.5. So write the expected value. So the expected value of this event, when all of the possibilities are considered, is 5.5. So contextualize means write down what this actually tells us. And since expected value is an average, we're going to start our sentence with on average. We don't want to say that they're always going to get 5.5 because that doesn't make any sense. It's on average, spinning this wheel, earns you $5.50. So should you spin this wheel? Well, probably depends on how much it costs you to spin the wheel. I mean, think about it as a game. At a fair or something, you would need to know what it costs to play. So if it's a $4 play, yeah, you should spin the wheel because you're going to earn more than that on average. If it's $10 to play, then no, it's not a good deal for you, and you're losing. Even if it's $6, you might not want to do it because on average you would earn less than that. All right, let's go back. I need to just clear this out a little bit here. Okay. So what we're going to say for this problem here about this raffle, we're going to look at the possibility of win 100 or win 25, right? So if we win 100, that's going to happen 0.00125. Winning 25 is going to happen 0.005. So if we multiply those outcomes, we could say that it's 0.00125 times 100 plus 0.005 times 25. And that is going to come out to, let's see, 0.125 here. And here it would be 125. 0.125 again. Okay, and if we add those together, we get a total of 0.25. So what this tells me is that the expected value of this event is 0.25. So what does this mean? This means on average, we earn 25 cents per raffle ticket. Now let's consider this. Should we pay this? Should we play this raffle? I'll go back and look. We buy a ticket for $2. We spent $2 and we're earning 25 cents. So is this a good deal for us? I mean, you could argue no mathematically, but again, there's more considerations than just the math of it. This is a fundraising raffle, right? So that right there is a good reason to do it. Even if you're expecting to lose money, that's overridden perhaps by the reason why you're doing it. So the math says no, not good. We're losing $1.75 every time we play, right? Every entry. But do we still want to do it? Well, that's up to you based on the context. Okay, so the overall takeaway of this, to calculate expected value, we're going to multiply the probability of the event occurring times the value of that event occurring over and over again until we run out of events, and then we add those up to see what the total expected value is. Expected value is an average. It is not an actual single event occurring. It is just an average over the long run. Okay, so from here you're going to go back to Google Classroom and work on your Amplify assignment.